Welcome to the Core Stream. The BYE podcast presents Matrix. Complexity reduced to logic, structured elements.
BYE Matrix, Episode 2, The Architectural Logic. Welcome back to the BYE Matrix. If you have returned for this second transmission, you have accepted the rigorous parameters of this deep tech immersion. Today, we bypass the philosophical abstractions and interface directly with the fundamental operating system of the universe, advanced mathematics. We are not here to simply count, we are here to comprehend the structural logic that dictates form, function, and continuous change. Prepare for a high-velocity download of absolute precision. The threshold has been crossed. BYE Matrix is now active. The foundational tenets of trigonometry and Euclidean geometry. Epistemological foundations, axioms, conjectures, and theorems. To truly apprehend the intricate architecture of mathematics, one must first delineate the epistemological framework upon which the entire discipline is constructed. Mathematics does not rely on empirical observation in the same manner as the natural sciences, rather, it is anchored in a rigorous hierarchy of logical deduction. At the very foundation of this edifice lie axioms, sometimes referred to as postulates. These are self-evident truths or foundational assumptions that are accepted unequivocally without requiring formal proof. They serve as the undisputed starting points for any mathematical system. For instance, a fundamental Euclidean axiom asserts that a straight line segment can be drawn joining any two distinct points. Building upon these axiomatic foundations, mathematicians formulate conjectures. A conjecture is an educated proposition, a mathematical hypothesis crafted through the observation of persistent patterns or intuitive leaps. It represents a statement believed to be true but which has yet to be rigorously proven or disproven by the broader mathematical community. When a conjecture successfully undergoes a process of rigorous logical deduction, utilizing only axioms and previously established truths, and is proven beyond any conceivable shadow of a doubt, it undergoes a profound epistemological shift. It transcends its hypothetical status to become a theorem. A theorem is a permanent, incontrovertible mathematical truth, standing as a testament to the power of deductive reasoning. The Euclidean heritage. Euclid of Alexandria, universally heralded as the father of geometry, fundamentally altered the trajectory of human thought by compiling the disparate mathematical knowledge of his era into a monumental treatise entitled Elements. His paramount contribution was not merely the collection of geometric facts, but the establishment of the axiomatic approach itself. Euclid introduced a systematic methodology for proving geometric propositions using nothing more than a compass and a straightedge. Euclidean geometry remains the absolute cornerstone of spatial understanding, governing the properties and relationships of points, lines, angles, and figures within flat, two-dimensional planes. The typology of triangles. A triangle, defined simply as a three-sided polygon, is the quintessential geometric figure, serving as the inescapable focal point of trigonometry. A fundamental theorem of Euclidean geometry dictates that the sum of the interior angles of any triangle will invariably amount to precisely 180 degrees. Triangles are meticulously classified through two distinct conceptual prisms, the length of their sides and the magnitude of their internal angles. When classifying by side lengths, we first encounter the equilateral triangle, a figure of perfect symmetry wherein all three sides are of strictly equal length. As a direct consequence of this physical symmetry, all three interior angles are also congruent, each measuring exactly 60 degrees. The isosceles triangle presents a slightly relaxed symmetry, possessing at least two sides of equal length. The angles situated directly opposite these equal sides are consequently equal in measure. Finally, the scalene triangle embodies asymmetry, as all three of its sides bear entirely different lengths, and inherently, all three of its interior angles differ in magnitude. Shifting the paradigm to internal angles, the right-angled triangle takes precedence, characterized by the presence of a single right angle measuring exactly 90 degrees. The side diametrically opposite this right angle is termed the hypotenuse, and it is unequivocally the longest side of the figure. An acute triangle is one wherein all three internal angles are strictly less than 90 degrees, whereas an obtuse triangle contains one defining angle that exceeds the 90-degree threshold. Determining the precise nature of a triangle requires empirical measurement of its side lengths or angles, or the application of deductive logic through specific theorems, such as utilizing the converse of the Pythagorean theorem to definitively establish the presence of a right angle. Pillars of classical geometry, Thales and Pythagoras. Before one can delve into the sophisticated realm of trigonometry, the monumental contributions of two ancient scholars must be thoroughly acknowledged. Thales of Miletus contributed several indispensable propositions to the geometric canon. His most renowned legacy is the intercept theorem, frequently referred to as Thales's theorem of proportionality. This theorem asserts that if a straight line is drawn parallel to one side of a triangle such that it intersects the other two sides, it invariably divides those two sides proportionally. Another crucial postulate attributed to his genius states that if three distinct points are placed on the circumference of a circle, and the line connecting two of those points constitutes the circle's true diameter, then the angle formed at the third point is inextricably a right angle. Pythagoras of Samos provided what is arguably the most ubiquitous formula in all of classical geometry. The Pythagorean theorem applies exclusively and fundamentally to right-angled triangles. It posits that the square of the length of the hypotenuse is mathematically equivalent to the sum of the squares of the lengths of the other two adjacent sides. This elegant theorem provides an infallible, deterministic mechanism for calculating the length of any unknown side of a right-angled triangle, provided the absolute lengths of the other two sides have been established. The advent of trigonometry. Trigonometry, a term derived from the Greek words trigonon, meaning triangle, and metron, meaning measure, represents a more advanced analytical framework. It fundamentally concerns the intrinsic, proportional relationships between the side lengths and the respective angles of triangles. Within the specific context of a right-angled triangle, if we isolate one of the acute angles for analysis, we can categorically define the three sides relative to this specific vantage point. The hypotenuse remains the invariant, longest side, resting opposite the right angle. The opposite side is the boundary situated directly across from the chosen angle. The adjacent side is the segment that, alongside the hypotenuse, physically forms the chosen angle. The trigonometric ratios. The fundamental tenets of trigonometry rely upon specific mathematical ratios established between these designated sides. Crucially, owing to the geometric principles of similar triangles, these ratios remain absolutely constant for any given angle, irrespective of the absolute physical size of the triangle in question. The sine function represents the exact ratio of the length of the opposite side divided by the length of the hypotenuse. The cosine function defines the ratio of the length of the adjacent side divided by the length of the hypotenuse. The tangent function is established as the ratio of the length of the opposite side divided by the length of the adjacent side. As mathematical inquiries become more complex, it necessitates the introduction of reciprocal trigonometric functions. The cosecant is the mathematical reciprocal of the sine. The secant stands as the reciprocal of the cosine. The cotangent functions as the reciprocal of the tangent. Mastering these fundamental, proportional relationships paves the critical pathway for comprehending substantially more complex mathematical architectures, including the mechanics of the unit circle, the behavior of periodic wave functions, and the intricate computations of calculus, thereby cementing trigonometry as an indispensable analytical tool across the entirety of the physical sciences. The algebraic architecture of computation, from foundational equations to advanced programming paradigms. At the very core of all computational logic and mathematical reasoning lies the elegant simplicity of the equation, a declarative statement of equality that challenges us to unveil the hidden truths concealed within its structure. The journey from abstract mathematics to advanced software engineering begins with the fundamental manipulation of equations harboring one or two unknowns. These are not mere academic exercises, they represent the foundational scaffolding upon which the sprawling architecture of modern programming is inextricably built. Equations with a single unknown, typically denoted by the ubiquitous x, serve as the deterministic bedrock of problem solving. They represent scenarios where a singular, unambiguous truth awaits discovery through systematic isolation. Moving a step further into complexity, equations with two unknowns, often interwoven into intricate systems, introduce the concept of multidimensional interdependency. Here, variables do not exist in a vacuum, their values are mutually contingent, requiring the solver to navigate through substitution or elimination to find the intersection point of multiple constraints. This leap from 1 to 2 dimensions is conceptually colossal, mirroring the transition from linear, single-threaded operations to complex, relational databases and concurrent algorithmic processes. To manipulate these algebraic structures with absolute precision, mathematicians and software architects across the globe rely on a rigorous procedural framework consisting of 4 fundamental operations: expand, reduce, order, and factorize. This robust methodology transcends its algebraic origins to become a masterclass in algorithmic hygiene and structural optimization for international engineering standards. Expanding involves the distribution of terms, dismantling parentheses to reveal the overarching mathematical landscape. It is the act of unpacking compressed data to understand the full scope of the variables at play. Reducing is the subsequent act of simplification, the meticulous gathering and combining of like terms. It eliminates redundancy, stripping the equation down to its most concentrated, potent form. Ordering introduces predictability, structuring polynomial expressions sequentially according to their degree. This deliberate arrangement transforms chaotic clusters of variables into logically parsable sequences. Finally, factorizing is the art of abstraction. By identifying common roots and extracting shared multipliers, factorization condenses sprawling polynomials back into elegant, modular components. When transitioning from theoretical mathematics to the tangible realm of advanced programming, these foundational operations of algebraic manipulation cease to be mere chalkboard concepts, they morph into the very syntax of computational efficiency. In software architecture, every line of code represents a consumption of resources, memory, processing power, and time. An unoptimized algorithm is akin to an unreduced, un-factorized equation. It works, but it labors under the weight of its own inefficiency. Consider the application of these principles in the development of sophisticated physics engines or graphics rendering pipelines. Simulating collision detection or calculating parabolic trajectories in a three-dimensional space requires the continuous, real-time resolution of complex systems of equations. The variables, velocity, mass, friction, coordinates, are the unknowns interacting within a strictly defined matrix of constraints. If the underlying mathematical models are not properly expanded, reduced, and ordered, the computational overhead becomes insurmountable, leading to catastrophic drops in performance. Furthermore, the concept of factorization finds a direct, powerful analog in the realm of software refactoring and algorithmic design. Just as algebraic factorization identifies common mathematical denominators to simplify an expression, software factorization identifies redundant logic across a code base, extracting it into modular, reusable functions or classes. This architectural abstraction not only reduces the overall memory footprint but fundamentally enhances the maintainability and scalability of the program. In the highly specialized field of cryptography, which underpins the security of modern digital infrastructure worldwide, equations with multiple unknowns and the principles of factorization form the ultimate defensive barrier. Algorithms such as RSA rely entirely on the computational asymmetry of factoring astronomically large prime numbers. The mathematical difficulty of reversing this operation, finding the original unknowns, is what shields global encrypted data from brute force decryption. Ultimately, the mastery of equations and the meticulous application of this four-step methodology cultivate a specific mindset, a paradigm of rigorous, structured thinking. For the advanced programmer, this translates into the ability to look at a sprawling, chaotic problem, systematically break it down into its constituent variables, eliminate algorithmic redundancies, and synthesize a solution that is not only functionally accurate but computationally elegant. Mathematics and programming are thus revealed not as distinct disciplines, but as two dialects of the same universal language of logic. The foundations and computational imperatives of differential and integral calculus. Calculus represents the mathematical study of continuous change, providing the rigorous foundational framework required to understand dynamic systems. Historically formulated in the late 17th century through the independent yet concurrent efforts of Isaac Newton and Gottfried Wilhelm Leibniz, calculus is bifurcated into two primary branches, differential calculus and integral calculus. These disciplines are intrinsically linked by the fundamental theorem of calculus, which establishes differentiation and integration as inverse operations. Differential calculus, the mathematics of instantaneous change. Differential calculus concerns itself with the concept of the derivative, which quantifies the instantaneous rate of change of a quantity with respect to another variable. Geometrically, the derivative of a function at a specific point corresponds to the slope of the tangent line to the function's curve at that coordinate. This concept relies heavily on the mathematical formalized theory of limits, describing the behavior of a function as its input approaches a certain value. Formally, the derivative of a function f(x) with respect to x is defined as f(x) equals lim h-0 f(x plus h f(x h). This elegant formulation allows physicists and engineers to transition from calculating average velocities over a macroscopic interval to determining instantaneous velocities at a precise, infinitesimal moment in time. Beyond kinematics, differential calculus is the cornerstone of optimization problems. By identifying the critical points where a function's derivative equals 0, practitioners can ascertain the local maxima and minima of complex multivariate functions, a procedure ubiquitous in fields ranging from economics to systems engineering. Integral calculus, the mathematics of accumulation. Conversely, integral calculus focuses on the accumulation of quantities, seamlessly aggregating an infinite number of infinitesimally small data points to compute a whole. Its most intuitive geometric interpretation is the calculation of the exact area under a continuous curve within a specified interval. The definite integral is formally defined through the limit of Riemann sums, which approximate the area by dividing the region into an increasing number of infinitesimally narrow rectangles. The mathematical notation for the definite integral of a function f(x) from a lower bound a to an upper bound b is expressed as integral from a to b of f(x) dx, While differential calculus decomposes a dynamic system to analyze its momentary behavior, integral calculus synthesizes these momentary behaviors to predict the total accumulated outcome over time or space. This is critical for computing physical properties such as center of mass, moment of inertia, work done by a variable force, and total fluid displacement. The intractability of analytical solutions and the necessity of computational machinery. While the foundational principles of calculus can be elegantly demonstrated using closed-form analytical solutions in academic settings, these ideal scenarios rarely manifest in the natural world. Real-world physical phenomena are predominantly governed by complex, nonlinear, and coupled differential equations, such as the Navier-Stokes equations in fluid dynamics or the n-body problem in orbital mechanics. For the vast majority of these equations, exact analytical solutions are either provably non-existent or currently undiscovered. Consequently, mathematical modeling must pivot from analytical exactitude to numerical approximation. This paradigm shift requires the discretization of continuous spaces and time intervals into finite, quantifiable grids or meshes. Techniques such as the finite element method, FEM, the finite difference method, FDM, and various Runge-Kutta methods transform intractable calculus problems into massive arrays of algebraic equations. Solving these monumental systems of equations requires arithmetic operations on a scale that drastically eclipses human capability. A high-fidelity weather simulation, for instance, might require solving billions of equations iteratively for every second of simulated time. Computational machinery, ranging from standard microprocessors to massively parallel hardware accelerators, is strictly necessary to execute these algorithms within a realistic timeframe. Machines provide the sheer brute force arithmetic throughput and memory management required to process immense floating-point operations without fatigue or error, effectively bridging the theoretical power of calculus with the chaotic complexity of reality. Prominent applications of computational calculus. The convergence of theoretical calculus and immense computational power has fundamentally revolutionized modern civilization. In the realm of aerospace engineering and orbital mechanics, computational calculus is non-negotiable. Designing the trajectory of a spacecraft requires solving continuous multi-body gravitational interactions while accounting for solar radiation pressure and atmospheric drag. Supercomputers continuously integrate these changing variables to ensure precise interplanetary navigation. Computational fluid dynamics, CFD, is another paramount application. Whether optimizing the aerodynamic profile of an aircraft wing, analyzing the turbulent airflow around a high-speed projectile, or modeling the atmospheric convection currents for global weather forecasting, CFD relies on machines solving the Navier-Stokes equations iteratively across three-dimensional spatial grids comprising millions of discrete cells. Furthermore, the contemporary explosion of artificial intelligence and deep learning is entirely predicated on differential calculus applied at an industrial scale. The training of artificial neural networks relies on the backpropagation algorithm, an application of the multivariable chain rule. The machine must calculate the partial derivatives, the gradient, of a highly complex loss function with respect to millions, or even billions, of synaptic weights. Specialized silicon processors compute these gradients simultaneously, allowing the network to iteratively descend the multidimensional error landscape and learn from vast datasets. Finally, in quantitative finance, stochastic calculus is heavily leveraged to model the random behavior of financial markets. The Black-Scholes-Merton model for options pricing, along with Monte Carlo simulations, requires computers to generate millions of randomized, differentiated price trajectories to accurately assess risk and value complex derivative contracts in highly volatile trading environments. To ensure your linguistic arsenal is equipped for this season, pay close attention to the following terminology. Epistemological relates to the theory of knowledge, specifically concerning its methods, validity, and scope. To apprehend mathematics, one must first understand its epistemological framework. Quintessential represents the most perfect or typical example of a particular quality or class. In classical geometry, the triangle is the quintessential geometric figure. Ubiquitous means present, appearing, or found everywhere simultaneously. The Pythagorean theorem is arguably the most ubiquitous formula in classical mathematics. Bifurcated describes something that is divided into two distinct branches or forks. The study of calculus is historically bifurcated into differential and integral branches. Intractability refers to the quality of being exceptionally difficult to manage, control, or solve. In physics, the intractability of analytical solutions often necessitates immense computational machinery. Congratulations! If you are still streaming this transmission, you have proven that you possess the intellectual stamina required for this journey. You are no longer just a passive learner, you are an active seeker of profound knowledge. The path to mastery is demanding, but it is the only path worth walking. While BYE Matrix explores the bleeding edge of technology and science, do not forget to engage with the rest of our ecosystem. Our standard episodes cover a vast array of societal and cultural themes. The BYE workshop provides hands-on linguistic refinement, and our special editions feature deep dive interviews with world-class experts like Luke Thompson. The grid is set. The code is running. Keep boosting your English. Bye for now.
Ready to boost your